Hello, we're just going to write a couple of functions to illustrate the parametric definition of a plane curve. So starting with our range, which will have, say, 40 units, and then the range itself starting from 0 with an increment of 1 and an end range of steps. The function itself, written for argument a sine curve of the range divided by the end range multiplied by a period of 2 pi and an amplitude of, say, 10. So we're going to plot this curve by entering, obviously, the value of the range in the placeholder of the independent variable and the value of the function in the placeholder of the dependent variable. And we're going to plot our curve. Now, we can increase the amplitude to scale the curve along the x-axis. And likewise, at the moment, the range A is from 0 to 40, as we've specified it over here. And this is what we've graphed on the x-axis. But instead of graphing the full extent of the vector A as it is, we could divide the independent range by steps and then multiply it by, say, half the range, which is 20, so that we can simply squash and scale the sine curve about the x-axis by 50%. So you see that we can intervene in the equation itself, but we can also intervene directly onto the graph to change the parameters of the independent range to gain full control over the scaling and the overall dimensions along the x-axis. So I'm going to create a second function now for the same range. So let's call this function k of a. And let us use the cosine function and let's assign it exactly the same variable, which is range A over the end of the range multiplied by a period of 2 and an amplitude of 20. I'm going to replace the value of the independent range at the bottom of the graph with that of the dependent function k of a. And that, of course, gives me the parametric equation of the circle. The circle of radius 20, which is the amplitude of the two functions that I have specified. I can scale that by down above, let's say, about either of the two axes. So I can scale the whole circle by 50% now with a radius of 10. Or I could simply scale it differentially in order to scale it, for instance, by, in this case, 50% along the y-axis only to produce a sort of ellipsoid. So as a follow-up, I would like to write the parametric equations of the line. Not that we will be using lines. Lines aren't useful at all in our context, but it's actually interesting to see how it is written and compare it to plane curves we'll be using, as well as see how we generally approach the parametric writing of a two-dimensional curve. So I'm going to create my range, which again will have 40 units. This time I'm going to call the range A as well, and write it from 0 to steps with increments of 1. I'm going to need 2 points to map my line. So I'm going to call the first point P1. And a point is, in MathCAD for us, there's various ways of doing it, but we'll be using a matrix right here of 2 rows and 1 column. So it's a column vector with 2 components. The first one is X and the second one is Y. Okay, so you can just type it here to list it. And should you want to extract the X or the Y coordinate independently, you just type the variable name and then use a subscript right here, which is this toolbar right there, and then use 0, which is the first element in any sequence, to extract the x-axis. So we can just type X over here, and then you can type P1, and then this time use subscript 1 to extract the second component of the column vector, which of course is y. Okay? So this is how you declare a point, and this is how you obtain its individual coordinates. So let us create a second point, okay, which we'll call P2. So I just copied and pasted the original value, and then this time P2 will have these coordinates, 10 for x and 20 for y. And having that, then I'm going to write the parametric equations of the line with obviously the right spelling. Okay, so for that I'm going to need three parameters. So it's the start point, which I'll call A, okay, the end point, which I call B, and then a parameter S between 0 and 1. These are the requirements for that. So having this, then we can just write the two parametric equations of the line, one for x and one for y. So the first one will be Lx, and as I explained, it has three arguments, which we can just call A for the start point, B for the end point, and then S for the actual parameter. Then hit the spacebar to wrap around the expression and assign it the following equation. So we start with the x value of the end point, okay, which is B0, which we multiply by the parameter, and then to this expression we add the following equation, which is 1 minus the parameter multiplied this time by the x component of the starting point. Write this, you see? So A0 is the x value of the start point, of course, and B0 is the x value of the end point. We can just cut and paste this particular expression to define the y component of the parametric equation, which is identical, except that obviously now we're going to be looking to use the y component of the end point as well as the y component of the start point right here, okay, using the different indices. So now that we have written our parametric equations, we need to put them onto the graph. So we can start by graphing Ly. So here we have to be a little bit careful. Remember, there's three arguments. The first one is the start point, which in our case we declared as P1, which is this point there. The end point is P2, and then the parameter, you see, we can't use the range A as defined because our parameter needs to be between 0 and 1, whereas A is between 0 and 40, which is very straightforward. All we need to do is make sure that as we pass A, we simply divide it by the end of the range so that domain from 0 to 40 is remapped onto a domain from 0 to 1. Likewise, we need to enter now the x component of the parametric equation, which has the same arguments, starting point, end point, and of course parameter S, which is in this case our parameter A divided by its end range. Okay, and then you see we get our line. So let us look at the line we've created. Let us try to make it say from this point there where my cursor is, which is 0, 20, and then let's make sure that it extends somewhere we can see it. Let's go to this point, which is 20 to 40. See? So now we get this nice diagonal line. The most important advantage of this way of writing the line, so you see it's quite a bit of writing for a simple line. It's not that practical, but there is a major advantage, which is that if we were to change now the end point to a value such as, say, 0 to 40, you see that we can graph a perfectly vertical line, which is not possible if you try to express the same equation using, for instance, a slope, because you can't have an infinite slope. So this is the most economical, the most effective way of actually writing a line. So you see, it's not that common. Okay? These are the two expressions that we need to remember. We won't be using them. It's actually a good example of parametric writing using the most familiar of primitives. Thank you very much.